I'm going to be talking about how to do a hypothesis test for two proportions using the birds on two islands problem. In Google Drive, if you look for the file entitled Key to Birds on Two Islands, and if you want to have that printed out or just be looking at that, I'll be talking about that version of the notes. The other version, Chapter 22, Part 2 notes that also says birds, is the same problem, but I did it a different year, and it's also really good, but it doesn't match up as exactly to the video. So they're both helpful. So I'm not going to read the problem, just quickly give you a quick overview. Basically, some researchers went to two different islands independently, tagged a group of birds on each island, and then after a period of time came back to the island and captured a random sample of birds, some of whom had tags on their legs and some of whom didn't. And the question is, does the data from that second sample, when they grabbed some tagged and some non-tagged birds, indicate that there's a difference in proportions of banded birds on the two islands? So we're going to set this up. This is a case where we have two different sample proportions, one from island A and one from island B. And our question is it possible that the difference between these two samples is great enough to say that there really is truly a difference in population of banded birds on each island? So we start out by saying, as our null hypothesis, there is no difference in the population proportions of banded birds on the two islands. In other words, the proportion A should equal proportion B. Since we need a number for our null hypothesis, we just subtract proportion B from proportion A, and we say the difference is 0, and that becomes our null hypothesis. Our alternate hypothesis is that there is a difference in the two islands. Now, how do we handle conditions here? We do our usual independence conditions of random sample and less than 10%, but we need to do it for each sample separately. So we're checking right now to see that we're checking for independence of the individuals within each sample and the individual birds. So we have a random sample of birds from each island, and we're going to assume that 180 birds is less than 10% on island A and 220 is less than 10% on island B. But we have to do a second type of independence now, and that is the independence between samples. We want, and this is the new, and this is something because it is unique to a two proportion test. If you leave this out, you will probably not get any credit for doing conditions on the AP exam, because this is the big one they're going to be looking for. Did you remember this one? You need to also say something like, we're going to assume that the populations of birds on the two islands are independent of each other. In other words, we believe that they're not flying back and forth between the two islands. Then we have to check a large enough sample, and once again, we have to check that each sample independently is large enough. And this is different from the other notes. I'm showing you actually both methods of checking this particular condition. You don't have to do both, obviously. In the event that you're given two samples and both the proportion of successes and failures in each sample is larger than 10, then just go ahead and use those sample successes and failures to check this condition, because that's easy to do. Now, in the event, though, and so that's what I would do in this case, and they all check. But sometimes you might end up with one of these four numbers being less than 10, and you say, oh, this is a problem. So then you go to the other way of doing this, and that is to create a pooled sample. And pooling is a very important concept in doing a two-sample proportion z-test, because our null hypothesis is that there's no difference between the two populations. So using that as our null hypothesis, then we can, for the sake of the model, throw all of our values together into one big happy sample, because we are saying we don't believe there's really any underlying difference between the populations of banded birds on the two islands. So we combine the two samples sizes in the denominator, we combine our number of banded birds in the numerator, and we say altogether out of the 400 birds, 47 are banded, and this is what's called our pooled sample proportion, p hat pooled, and then that would be q hat pooled. And so we can use p hat pooled and q hat pooled to check the large enough condition for both samples. So we take the 220 and the 180 times the p hat pooled and the q hat pooled, and we notice that all of these are greater than 10, so it would pass. So this method method 2 is always correct to use, but if you don't, and notice it gives us larger values for our successes than we had using the samples. So the sample, if the sample's large enough, then we can be pretty well assured that the pooled values are going to be large enough too. So we don't need necessarily to do the pooled values if these are already okay. So that's the idea here. So now we say we can use the normal model for the difference of two proportions to do a two-proportion z-test. Now when we look at how we do our work, I brought over these pooled values because these are going to be very essential to use in the rest of the problem. So even if you don't pool to check your conditions, you're going to need to pool to do the work in the problem. So here we have our p hat for island A and our p hat for island B, and the difference between the two is negative 0.092. So what we're trying to find out is that far enough away from 0 to reject 0 as our null hypothesis. And because we're saying is it different, and we're looking, oh, that actually should be a positive here, and I probably have that wrong in the printed notes. So in other words, are we either negative 0.092 or positive 0.092 away from the origin? Either one of those would be extreme enough, would be equally extreme, and we want to know, together, are they far enough away to reject the null hypothesis? So the probability that p hat A minus p hat B is at least 0.092 in either direction would be 2 times this normal CDF. Now, if we do 1 times the normal CDF, this is 0.002 and this is 0.002, and together it's 0.004. So we have a very small p-value, which means we can reject the null hypothesis. I think I kind of left something out here. How did we get sigma? Okay, we haven't really talked about how we get sigma. The way we get sigma is not just using p hat pooled, q hat pooled divided by n. We have to do it differently, and this is really important, and this is another thing that sets this test apart from other tests, and that is how you find the standard deviation. And you'll find that the standard deviation is kind of the signature for each particular type of test. They all have a slightly different standard deviation, and so the way we do this one, the mu of p hat minus p hat A minus p hat B, the mu of all of these differences would be 0, because that's what we're saying for our null hypothesis. The sigma, however, what we do is we add variances. We say that we're using our p hat pooled and our q hat pooled for both samples because of the one big happy sample thing, but we have we put them over the denominator separately, and we say this is actually the variance. Remember, variance is standard deviation squared. So if we think about this, standard deviation of p hat is square root of pq over n. Variance of p hat then would be pq over n without the square root. So here's our pq over n and our pq over n for both samples. We add those together and then take the square root of the whole thing, and that's where we get the 0.032. Now, the nice thing about this is, actually, no, it doesn't show. Shoot, I wish it did. The test on the calculator does not automatically compute that for you. You have to be able to compute this to show that you know how to compute this as part of your work. And you don't really have a check on that. However, you could figure out what it was sort of in the backwards, because you do get a z-score. You know that your p hat A minus p hat B, your sample statistic, is negative 0.092. You know your null hypothesis is 0, and you know your z-score, so you could double check your work by figuring out what the standard deviation is here if you needed to. So doing this all in the calculator, automatically, this one, when you do it using the normal CDF, you have to remember to double it because it's a two-tailed test. When you do it on the calculator as a two-tailed test, the not equal to, it automatically doubles it for you, automatically calculates the p-value. So here's our p-value. And our conclusion. Interpreting p is a little tricky on this. When we interpret p, we say since p equals 0.004 is less than alpha, we reject the null hypothesis and conclude that the population of banded birds on island A and on island B are different. Now here's the interpreting p. There is less than a 1% chance of obtaining the observed sample difference, of 9.2% or more So it's a difference of that, a difference of 9.2% or greater a difference if the two population proportions, that probably should be an S, were actually no different. Okay? So if there was really no difference between the two, there would only be a 1% chance that we would see this much difference or more. The samples indicate, now, the last sentence is, when we do a two-proportion test, usually our null hypothesis, or often I should say our null hypothesis is that they are equal, and the alternate is that they are not equal. But we do notice that one of the samples had a higher population proportion than the other. Island 2, Island B, had a higher population proportion, or had a higher sample proportion. So we can then say the samples indicate that Island B has a higher proportion of banded birds than Island A does. Okay. And I probably should put that Island B probably, because there is variation among samples, and it's possible that we could have gotten an unusual set of samples there, but probably has a higher portion of banded birds than Island A does. So that would be your conclusion. Let me talk about part C and D. However, if you haven't tried them yet, stop and do those first before you actually listen to this. In part B, how do you estimate the total proportion of birds on the island from just one of these samples? Well, in the beginning part of the problem, in the information given, it says that they banded 200 birds on Island A. And then when they came back, so out of all the total birds, 200 out of X birds were banded. When they came back, they got a sample of 180, and 12 of them were banded. So assuming, and this is kind of a big assumption, but assuming that the birds kind of randomly scattered their way back through the population, not like, for example, all the banded birds didn't all just cluster in one part of the island, but they flew around and got all mixed up with the other birds, then we could set up a proportion and say 12 out of 180 equals 200 out of X, and so we would say the population would be about 3,000 birds. And this is actually the way, this recapture method is actually the way that naturalists often will estimate the population of a wild animal, is by doing this very procedure. Then part C says, what assumptions do we have to make to even do these inference tests? So what you want to think of is, think of a common sense reason, and then how does that apply to a statistical reason? Okay, so common sense reason that we might have problems. Birds could die or be born between samples. The population could be changing. So the sample may no longer represent the original population of banded birds. The banded birds might differ from the unbanded birds in some way. Maybe they're slower, maybe they're sick, easier to catch, shunned by their relations or whatever, so they wouldn't represent the population. Maybe it would be easier to recapture them because they were the ones that got captured in the first place. So once again, they aren't representative of the population. The assumption that birds return to their original routine and location might not be true. Maybe once they're banded, the other birds won't hang around them anymore, and so they kind of are isolated in one part of the island. So once again, the sample might not be well mixed, and so it might not represent the population. So the big idea here obviously is that our sample of 180 birds might not represent the population of birds on the island for one of these reasons. So you get to give one of these reasons and then explain that it might be an unrepresentative sample because of that. So hopefully that's helpful to you as far as going through this problem. If there's anything you don't understand, please ask in class about this.